All right, I think we're good. Okay, so the first thing, like I said, we're going to talk about today is defining a function. So I'd like to start with you guys just telling me some things that you remember about functions. Not like the properties and the detail stuff, but just kind of in general, like what do you remember, like, what is a function? Start there. Oh, okay. It's called the vertical line test. Yeah, pass the vertical line test. Okay, so that's if we're looking for functions on a graph. Okay, that's a way we can do that. But why do they pass the vertical line test? That's kind of at the heart of this. That's what their definition is. Think about what the vertical line test looks like. The way that you do that is you're looking for, if you put a vertical line through a graph, it should not touch the graph more than once, right? If you have a vertical line intersecting your graph more than once, it's no longer a function. Why is that the case? Yeah?
They don't have the same x.
Right, yeah. There can't be two y values with the same x. Okay? So it's an input-output kind of idea. But so think of x as input and y as output. Okay? So for every one input x, you can only have one output y. You can't plug a number into a function and then like get two answers, right? It's not a function if that happens. So based on that vertical line test, the definition is for every one input, which is usually x, there is only one output, which is usually y. All right. Now the input and the output have special names, and we'll start referring to them as these throughout the year. The input we refer to as the independent variable. And the output is the dependent variable. Okay, why do you suppose they're called independent and dependent? Yeah, that's exactly right. The y variable changes as the x changes. Okay, we can set x to be whatever we want, but y, the output, depends on the input, right? So the value of y, of this, depends on whatever number we put in for x, our input. So that's why we refer to them as independent and dependent variables. Later on, as we get into some more complex stuff like differential equations, etc., this idea of independent and dependent is going to come back around. It's going to be really important for us to understand. So good to get it out now. Okay, so that's what a function is. So let's do a little review about some domain and range. So pre-calc, we talk a lot of domain. So what is a domain? Okay, what about the x values? It's the ones that work, essentially. I think you guys both had it kind of together there. So they're the x values for which a function is defined. Or the way we kind of described it in pre-calc was, they're the x values that work, that you can plug in. And range, same idea. What's the only difference with range? They're the y values. Okay, now, caveat here. It doesn't have to be x and y necessarily, right? Technically, domain refers to the independent variable and range refers to the dependent variable. But I'm going to use x and y just as kind of a generic way of describing it right now. Okay, so can we calculate domain? In pre-calc, and it's going to be the same in calculus, I'm going to expect that you can do a domain by hand and a range as long as you have a graph to look at. Okay? And in calculating a domain, there were really only 3 issues we ran into that might affect a domain. Otherwise, it would just be negative infinity to infinity every time. It'd be all numbers, all real numbers. Anybody remember what those 3 things were that we kind of looked for to see if there was any kind of a problem? I don't think so. I think you're thinking more of like if it's not a function or is a function. So this is, we're already assuming it is a function. It's just what might cause a gap in the domain somewhere. So think about asymptotes. Okay, so yeah, first thing we're going to look for, does it have a vertical asymptote? Which is created by dividing by 0 in the function. Okay, so those are real easy to see. Does your function have a fraction in it, in which the x is in the denominator somewhere? Okay, so that's one issue. Anybody remember the other 2? Or one of the other 2?
At this time, sophomores are due to obtain their netbook. Please go to the front door. Thank you.
All right, I'll give you some help here. Square roots. Okay. What do we know about square roots? For what numbers are they defined? Yeah. Correct. You can't take the square root of a negative number. At least, not unless you're considering imaginary numbers as part of your solution, but for this stuff, we're not. So, square roots, yeah. Can't square root a negative. So there could be a gap in the domain because of that then. Okay, if you had a square root as part of the function, just make sure whatever's underneath that does not come out negative. And then the third one, which most people forget about, would be logs. Whether it's a natural log or a common log or whatever, these guys have only certain numbers you can input into them as well. Anybody remember what it is about logs? Only positive numbers. Yeah, it's very similar to the square root situation, except 0 is not in play for a log, right? You can't do the log of a 0. You can do a square root of 0, though. So you can't log negatives or 0. Okay? So, you just got to try to identify if one of these 3 or more than one, or any combination of these are happening in the function you're looking at, and then you can kind of go from there. So let's try that a little bit. We'll do a little bit of domain calculations by hand here. Okay, so let's say we've got the function 3x times the square root of x minus 5. So which, if any, of those 3 things that we talked about do we have in this one? There's a square root. Okay. And so we're going to ask ourselves, what numbers can I plug in for x into this square root? 5 and above. Right. Okay. So you got to be careful because it's not just 0 and above, because if you put a 0 into this, it would make the square root -5, and we can't do that. But if you start at 5, then you're good. So our domain for this, and you do include the 5, right? Because square root of 0 is still defined. So it is from 5 to infinity, including 5. And remember, you always put parentheses around your infinities, right? Because you can never actually get to infinity. All right, let's try another one. Let's do g of x equals x plus 2 over x minus 4. Okay, so which of any of those three issues do we have here? It's a dividing by 0 issue. So what number is going to make this thing not work? 4. Okay, so our domain then is going to be everything except for 4. So negative infinity to 4, union 4 to infinity. Okay, remember, if you got more than one interval, you put the little u in between them for union. And that would be that one. All right, we'll do one last one here. How about log x over x plus 2? So what's going on in this one? Yeah, there's two things, right? You got the log situation, and you got x in the denominator of a fraction, so that's going to affect the domain as well. So start with the log. What numbers are we restricted to with the log? Can't use negatives and 0, right? So it's just positive numbers then. So this function already, we know positive numbers are all the ones that we're going to be able to use. What about the denominator, though? Right. So here's what we got then, to summarize. We've got only positives can go on the top, and any number except for -2 can go on the bottom. So what then is our domain? Just positives, right? Because this -2 doesn't affect anything, right? We already have excluded -2 from the top using the log, so we don't have to worry about it. Now, that being said, what if this had been an x minus 2 in the bottom? Then you have to exclude +2. So you got to hop over it as you're doing all your positive numbers. But in this case, though, we can stick with just a domain of 0 to infinity like that. All right. Now, identify range. I said we're going to have to just do from a graph. Okay? So what I'll do then is I'm going to draw some graphs for you and see if you can tell me what the range is of each one of them. Okay, I'll just leave that one like that. So I'll give you a second to copy those down. All right, so that first one, what's the range? What y values is that function defined for? There you go. Yep, 1 to infinity, not including the 1. So a range 1 to infinity, because of that asymptote, we don't include the 1. Okay, yeah? Well, if it were, like the fact that it's an asymptote, we know for sure it doesn't include 1, because it's never going to actually reach it. If it was something like, if I drew it, like let's say it was a parabola, and I had it come down like this, do something like that, where there was actually a point right there, then we know it's actually going to hit 1 and come back. But yeah, the asymptote kind of gave it away for this one. Okay, the second one, what's the range? Negative infinity to infinity. Keeps going up, keeps going down. It's going to hit all of them. Good. Okay. And as we get into some of the piecewise function stuff later, we'll do some more of this kind of thing with the graphs. But just wanted to make sure you guys were still thinking this way about range. Okay. Symmetry, real quick, we'll do next. Okay, we got two different kinds of functions when it comes to symmetry. We call them even and odd. Bless you. An even function is if f of negative x equals f of x, is the definition of that. And an odd function if f of negative x equals negative f of x. Now this you probably don't remember, but identifying them on a graph you probably do, okay? Because that was a little bit easier to see what was going on, because there's some distinct characteristics for each of these. So, about even for a minute here, okay? To be even, negative x has to equal f of x. So let's say at negative 1, my function is up at a value of 2. What does that tell me about the value of the function at 1? It has to also be at 2, right? F of negative x equals f of x. F of negative 1 equals f of 1. So they have the same y value, right? So this one also has to be right there, okay? Say at negative 2, my function is at 1. So what has to be true about f of 2 then? I think I heard somebody whisper it, but what has to be true of f of 2? What's the value? 1. Yeah, it's got to match the other one, right? F of negative 2 equals f of 2. They have the same y value. Let's say at 1/2, we're at, or negative 1/2, we're down at 0. So at positive 1/2, we're at 0. Negative 1.5, maybe it's at like 2.5. So positive 1.5, it's at 2.5. Okay, So, and then maybe at 0 we're like down here or something at -1. So the point is, though, as you start to kind of sketch this thing together, what do you notice about the shape of it? Okay, so it has kind of this, it has this kind of reflective quality then, though? They have to both be going towards the same thing in the middle? Okay? Any even function will do that because of the nature of this, right? Whatever the negative number is here, the positive number on the other side has to have the same y value. So you create this symmetry, okay? There's a line of symmetry with even functions down the y-axis, okay? So the one way that we were checking for even functions last year was, can you reflect it around the y-axis? Okay? So, give myself a little more room here. So if it's even, it has reflection symmetry about the y-axis. So that's a real quick way on a graph to identify if something is even. All right, now odd, it's kind of the same game. I'll make this one a little bit bigger. Okay. So with an of negative x equals negative f of x. So let's say I have at -1, I'm up at 2. So if it is odd, and f of negative x equals negative f of x, what should be the value of f of 1? -2. Mm-hmm. So it's going to be down there. All right, so let's say at -2, I get a value of +1. So what's the value of f of 2? -1. Mm-hmm. And if, let's go out one more. So let's say at -3, we've got a value of, oh, how about -2? Then what's the value of f of 3? Positive. Yeah, +2. And then maybe like 0 is 0. So then this one starts to take on this kind of a shape. Okay, so with these don't have that line of reflection anymore, do they? Okay, if I were to take like this half and reflect it over, it's not the same, right? What did we say about odd functions, though? What's the way that you can kind of think about them in your head to check? What was it? Yeah, it's got rotation symmetry to it, okay? If you rotate it 180 degrees, it should be back on top of itself again. So like this maximum point would swing around to where this minimum point is and vice versa and everything in between, okay? So odd functions have rotation symmetry. So we say it has rotation symmetry about the origin. Okay, so that's even and odd. All right, just a little quick review. Do you guys remember why they're called even and odd? We did kind of a little investigation like halfway through the year last year talking about that. All right, I'll see if you can figure it out here. Think polynomials. f of x equals x squared, parabola. Think about it. What kind of shape does it have? Is it even or odd? Even. X cubed. Think about the graph. Is it even or odd? Odd. See where this is going? Okay. So x squared is even, x to the cubed, x to the third is odd, x to the fourth is even, etc., etc., okay? It came from a study of polynomials, okay? There was somebody, I don't know who, that was initially studying polynomials and looking for properties of those and recognized the symmetry effect that was happening to every other one. And so just started titling them that. There's the even functions, there's the odd functions. But then that idea could expand to other functions that didn't have powers that were even or odd numbers. So that's kind of a little backstory for you with that. But so knowing what your graphs look like, though, your 12 basic functions that we talked about last year, that's going to be increasingly important too this year, because sometimes you're only going to be given an equation and you're going to be asked to identify, is it an even or odd? So if you know what the basic shape is based on its parent function, and then if it's been, transformed in any way, then you can identify what kind of symmetry it has as an even or odd function. So you'll be doing a bit of that in your homework as well, is doing some of that identification stuff. Piecewise, I think that's where we'll finish up here today. A couple that you guys will be asked to do with piecewise functions. Graph it. And then also, could you take a piecewise function and write an equation for it? Can you go back and forth with that? Okay. So, start you off with one here. Okay, let's start with something like that. So f of x is defined as x squared on the domain 0 to 2, and it's 4 on the domain 2 to infinity. Okay? So, one thing to check here, this is indeed a function. I made sure. If I had put a bracket around this first 2, and then a bracket around that 2, it wouldn't be a function anymore. Why not? You could potentially have 2 different y values for 1x then, depending. So when I'm at 2, am I looking at the first piece or am I looking at the second piece? I don't know which place to go. Okay. So when you create these things, you have to be careful about making sure that you don't overlap a number. So if it's a parenthesis on one, bracket on the other.
Juniors, please come receive your netbook. Juniors, come to the front main door.
All right, we'll see you guys in a little bit. Okay, to graph this thing, I tried these 2 functions that are inside of this thing, fairly straightforward. So, and we're only starting at 0. So this thing is actually all contained within the first. Okay, so from 0 to 2, it's going to look like a parabola. Okay, well, when that parabola gets to 2, what value does it have? So it's going to end up here. Okay, and when the parabola is at 0, the beginning of its interval, what's its value? Plug in a 0, what do you get? 0, right, okay. So it's going to be a parabola from 0 to 2, but don't put the arrowhead on the end of it, because it's just a piece. It's not the whole thing, right? That's why we call it a piecewise. We've taken a piece of that parabola and just, we're using that. That's it. Okay? Now, from 2 to infinity, the function has a value of 4. What does f of x equals 4 look like? Yeah, it's just a straight horizontal line of 4. Okay? So, starting here, has a value of 4. Just going to head over. And this one we can put the arrowhead on because it's going to infinity. So that graph would look, yeah, something like that. Is that a continuous function? Yes, it is. Okay. Do the two pieces connect? Yes, they do. Okay. Is there any kind of a gap in it at all on any of the two pieces? Nope. It's a whole continuous piece of the parabola. It's a continuous piece of that line. They connect up. Yes. Some piecewise functions will not be continuous. There'll be like a jump or a gap or something in between, depending on what we're working with. Okay. So let's try one more. I'll try and make this one a little bit more difficult and see if we can produce a graph. And then I'll have you go the other direction with it. Okay. So let's do 2 minus x squared for negative infinity to 0. And let's include the 0 on that one. And then we'll do one plus x from 0 to 4. Include the 4 on that one. And then how about negative x plus 9. Yeah, that'll work. Okay, so I got 3 pieces, 2 minus x squared, 1 plus x, negative x plus 9. Each of those individual functions that are kind of embedded in there, you should have an idea of about what those look like. Okay? That's all stuff from what we did in pre-calc last year with basic functions. We got one that's a parabola, 2 that are lines. Okay? And kind of knowing about the properties of each of those to be able to sketch them out. So this one goes a negative infinity to infinity with 3 little chunks that are putting it all together here. So we're going to start with the first piece. And this one will need the whole coordinate plane to do it. All right, so that first piece is from negative infinity to 0. It's going to look like the parabola 2 minus x squared. Okay, so let's at least get like the right endpoint. So at 0, where does that? What's the value of that parabola? 2, right? You plug in a 0, you get 2. So that parabola is going to be here at 2, and that's a bracket, so it will get there. So I'll put a solid dot there. And then what do you know about this parabola if it's 2 minus x squared? So from negative infinity to there, what should it look like? Right, it's a parabola but going down. Okay? It's just the side of it, right? So it's this. And you can put an arrow on the end of that. Okay, that's fine because it's continuing to negative infinity that direction. Okay, so from 0 to 4, it's going to look like 1 plus x. So let's get both sides of that. So if you plug in a 0 into that, what's the value of it? 1. And is it actually getting to that number, though? It's got a parenthesis there, right? So we're going to open circle that one. Because the function at 0 is actually defined on the top piece, right? Not the middle piece. So that's an open circle. Where does that little line segment end up, though? What value? Up at 5. So once we come out to 4, it's supposed to be up at 5. Oops, I got to extend this up a little bit then. Okay, so 4 is going to be over at 5. And that is a solid circle, right? Because that's got a bracket on it. So then we'll connect those together. So it looks like that. And then from 4 to infinity, it's negative x plus 9. So start with the 4 again. If you put a 4 in, what do you get? Okay, so this piece is connected, right? So it's going to start at this point again. And then it's negative x. It has a slope of negative 1 from there. So that's going to come down like that. So, looking at this whole thing, is this a continuous function? Okay, not all the pieces connect up, right? There's this little gap here between those two pieces, all right? But that's what that graph would look like. Real quick, let's just do one where you have to look at the graph and then write a piecewise for it, and we'll be done. Come on. All right, so say we got that, and then okay, so let's say we got that graph, and we are tasked with coming up with a piecewise defined equation for that. So, first things first, how many pieces do we have? 3. So when we write out our equation, we need to make sure we leave room for 3 pieces. Okay, so the first piece is part of a line. What's the equation of that line that it would be a part of? Be just x, right? What's the slope of that line? 1. What's the y-intercept? 0. So it's just y equals x. So we would just put x. Okay, you don't need the y equals x, because the y equals is already taken care of with this f of x in the front here. So it's just x. Now, we also have to give it a domain, though. What x values is this piece defined for? So from what to what? Exactly. 0 to 2, not including the 2. So like that. That'd be the first piece. Okay. I guess for this one I better make sure you can see that part clearly. Okay. So second piece, what would be the equation of it? Be just 1, right? Y equals 1. So 1. But again, what's the domain? I think I heard somebody whisper it. What is it? From what to what? 2 to 4. Okay. Do I include the 2? Mm-hmm. Do I include the 4? I can if I want to. I don't have to, though, technically. The 4 has to be included in one of those 2 pieces that connect. Not both, though, right? Just one of them. So, what the heck? We'll do it right now. Okay. So then we can't include the 4 in the last piece, though. Okay. Okay, so the last one is another piece of a line. Okay. What is the slope of the line? -1. So I know I've got negative x, and then what would be the y-intercept? It would be 5, right? Because if you follow that pattern back to the y-axis, it would be up at 5. So it's -x plus 5. Though we never actually see that line cross the y-axis, right? It does have a y-intercept in its equation, but it's just a piece of it, right? So it doesn't actually get there. All right, and then what's the domain for this one? 4 to infinity, but we can't include the 4 because we did in the last piece. Okay, so that would be the equation for that piecewise. Okay. All right, stop there for today. Tomorrow we'll pick up the rest of the stuff. Or not tomorrow. Monday, or actually next week, Wednesday, or whenever it happens to be. But eventually. Alrighty. We're going to finish up with section 1-2 here. Like I said, the only 2 things we need to go over are absolute value and composite functions. And, okay, so what do you guys remember about absolute value? What is it? Yes? It looks like that. Yep, it looks like a big flying V when you graph it, but what is it? What does it do? You input a number into absolute value, and what does it do to it? It always makes it positive, okay? And the reason that absolute value always makes it positive is because the function of absolute value is to calculate the number's distance from 0. And distance is always positive, right? So if it's a positive number, it just returns the same number. If you give it a negative number, it'll turn it positive because that negative number is that distance away from 0, okay? So it measures distance from 0. And as a result, always returns a positive number.
If you had to pick your favorite function, would it be absolute value?
My favorite function?
Your favorite
No, not absolute value. My favorite basic function. I'm a big fan of the square root. Yeah, it's a good one. All right, another way to define absolute value then, I mean, usually we just write it, like with its symbol, f of x equals absolute value of x, like that. But because of its definition there, though, we can define absolute value as a piecewise function. And this is going to be important later on when we start talking about derivatives and things. So think about absolute value in 2 pieces. Okay, so if the number that I'm inputting into it is something negative, it's following the function negative x, and if I input into it something positive, it's following the function just x, and that's why you get that flying V kind of look at the graph, it's really two linear functions put together, right? It's negative x as it comes down the one way, and then it's positive x as it goes back the other way. So it's really a combination of those two things. Now, where do you put 0 in here? Well, technically it doesn't matter. You could put 0 in either category and it would still work. So I think kind of the more accepted way of doing it would be it's negative x for x less than 0, and then positive x for x greater than or equal to 0. But technically the 0 could go either place. Okay, so might ask you to like sketch a graph of absolute value, or take a look at absolute value and an equation and draw a graph, or look at a graph, come up with its equation, that sort of thing. Domain, range, all that kind of business. So let's analyze an absolute value function here. So let's say we got f of x equals absolute value of x minus 3 plus 1. All right, and we need to, let's come up with the graph, find its domain, and find its range. Okay, so we're going to focus on those three things. So the graph of this, if we start with just what the graph of a regular absolute value looks like, this is simply just a transformation of that, right? It's had some movement. So all right, so a regular absolute value graph. I'll put a little color on here. So we said that, thinking about this little piecewise definition here, it's negative x as long as we are, oops, make this a little straighter. All right, so it's the function negative x if we're less than 0, and it's the function positive x if we're greater than 0. So it looks like that. So this new one, though, this x minus 3 plus 1, like I said, is a transformation of that. So how has that been transformed? Is it a stretch? Is it a shrink? Is it a shift, left, right, up, down? All right, so we have some shifting going on, right? So in what direction? Raise your hand maybe, and I will call on you then. Okay, Rachel, go ahead. Up 1. Okay, yep. And to the right 3. Good. Remember, if it's on the inside of the function, okay, then it's always the opposite of what the sign is. If it's on the kind of the outside, then that's going to be the same. So this is a right 3, up 1. So that means I'm just going to take this thing and translate it. So now, kind of like a parabola has a vertex, absolute value has a vertex. So a normal absolute value, or the parent function, has a vertex at 0, 0. The new vertex now is going to be at 3, 1. And then it's all the same from there. So it heads up that direction, and it heads up that direction like that. Okay, so that's your new one. So we're able to produce what the graph looks like there then. And then from that, we can do the domain and range pretty easily. Okay, now the domain. This is true of any absolute value function. Whether you've stretched it, shrunk it, translated it, up, down, left, right, what should the domain always be? What numbers are okay to plug into an absolute value no matter what? It's all real numbers, negative infinity to infinity. Yep, all of them. Okay, remember with domain, there's only 3 kinds of functions that are going to give you any kind of something different than this. And that's if it's a reciprocal type function where you're dividing by 0, a square root because you can't take a square root of something negative, and logs because you can't log something negative or 0. Okay, so absolute value, domain, negative infinity to infinity, it's all of it. The range, that will be something different. And with the translation, it affects it as well. So look at the graph. What's the range here? 1 to infinity. Good. And do we include the 1? Yes, because it does actually get there. So my suggestion would be, because they're probably going to ask you for both domain and range here without a calculator, but knowing what you know about the absolute value graph, do the graph first, then you can easily answer the questions about that. Okay? If you try to go after the range without looking at what the graph is, it's going to be pretty hard. So, okay, good. Let's transition. We'll go on to composite functions next. Do a little review over those guys. So what do we remember about composite functions? What are those? Oops. There we go. Okay, so what do we remember about that? Everything. Good. So tell us, Rachel. You might as well just teach the class. It's fine. No, what are they? What's a composite function? It includes multiple pieces. Yes, true. In what way? Do we need a little help?
Yeah.
Okay. F of g of x and g of f of x, that type of thing, those are composite functions. When you take one function and you substitute it into the other function for x. Okay, so for example, let's say f of x is x squared plus 2x and g of x is x minus 1. So then if I did f of g of x, okay, you can kind of see the substitution right in the nomenclature there. Or notation, I guess maybe is the better word. So then the g of x is going to be substituted into f of x for every x. So it would become then x minus 1 squared plus 2 times x minus 1. And then you could do some simplification from there if you wanted to, FOIL out the x minus 1 squared and distribute the 2 and all that business. But at the end of the day, though, that's still the composition f of g of x. And then you can go the other way with it, too. So if you wanted to do g of f of x, that would be taking the f function and substituting it into the g function everywhere you see an x. So we only have one x in the g function, so this entire thing, x squared plus 2x, would get dumped into x right there. So we'd end up with x squared plus 2x minus 1. Yeah, it would just look like that then. Okay. F of g of x and g of f of x will not necessarily come out to be the same thing. Sometimes they do. Most of the time they don't, though. Okay. So this is kind of a input-output type thing. Again, we're talking functions, right? So there's, if you're going to do f of g of a number or g of f of a number, it's a situation where the output from one function becomes the input for the next one. Okay? So if I wanted to find, let's say, f of g of 2, okay, a couple different ways I could go about doing that. If I wanted to go directly to my composite function, f of g of x, I could just plug a 2 directly into that and be done. Okay, crunch it out, see what I get. Otherwise, think of it this way. You're going to do 2 as an input into g, and you're going to get an output from g. And then that output from g becomes the input for f. So you got to figure out what's g of 2, and then use that number into x. So take a look at g of x. What is g of 2? 1, right? So f of g of 2 is the same thing as f of 1. Does that make sense? So that output that we got, 1, from g, is now our input for f. So f of 1. And then we can just look at the f function. Okay, what is f of 1? 1 squared plus 2 times 1. What do we get? 3. Okay, so that is 3. So think of things kind of that way, and I think it makes it a little bit easier when you're crunching numbers. Just while we're doing it, might as well go the other way too. So what is, let's say, g of f of 2 as well. Go the other way with it. So start with f now. Okay, we always kind of work inside out with these. So what is f of 2? 2 squared plus 2 times 2. 8, okay. So that's going to leave us with g of 8. And if I plug an 8 into the g function, what's the answer then? 7. Yeah, 8 minus 1, 7. Okay, good. Let's see. I think that's all we need to do with those guys for now. We'll talk more about composites later, but I think we're good. I'm going to stop the recording.